Just a couple more examples of the multiplication rule. So remember earlier in the course we talked about the idea of hexadecimal, and then we also talked about binary code. So sometimes what we'd like to do is we'd like to be able to figure out how many different ways there are to arrange the hexadecimal words as well as binary words. So just as a reminder, in hexadecimal there are 16 total characters. Okay, and if you remember, 10 of those characters are digits, and then 6 of those characters are letters. So it's helpful to know before we go on and try to solve the problem. Right? So, how many different hexadecimal numbers, all right, and when we say numbers, think about hexadecimal number as like a word, okay, that begins with a number, ends with a letter, and are 4 characters long, both with and without repetition. All right, so for letter A, so we have 4 characters with repetition. Okay, so it begins with a number. So we know that there are 10 possible numbers. It ends with a letter. All right, so if it ends with a letter, then we know that there are 6 possible letters. It doesn't matter what's happening in the middle there, okay, because repetition is allowed. So there are 16 possibilities if repetition is indeed allowed. So we're going to throw that into our calculator, and I end up with 15,360. Now what if repetition is not allowed? Alright, so we still have 4 characters, and here's the way you want to try to think about this. It doesn't necessarily matter when the characters are picked because it's multiplication. Multiplication is both commutative and associative. So whenever you're doing these types of problems without repetition, always try to pick on the things that are a little more restrained. Okay, so in other words, there's more constraints with the first character and the second character, or the last character, excuse me. So how many different hexadecimal numbers begin with a number? All right, so we haven't done any sort of restriction yet. So there's still 10 numbers, and then it ends with a letter, right, which is still 6. Notice that this is the first one's a number, and the last one's a letter. They're completely independent from one another. Now what we've done is we've taken the 16 and we've taken 2 away. So now there's 14 characters left. So it doesn't matter what's in the middle. It could be a number or a letter. So I'm just saying number or letter, N-O-R-L. So there's 14 possibilities. Whatever we've picked, we don't know if it's a number or letter, we've picked one, and now there's only 13 possibilities. So again, it doesn't matter the order in which they're selected, and this is generally how a computer algorithm goes through, is it picks the most constrained characters first, and then it goes over to the other ones. A lot of times, like if you're playing a game like Words with Friends or Scrabble on your phone, this is how the computer might algorithmically generate the best possible word that could be created from a number of different tiles or a number of different letters. So I'm going to go ahead, compute this. I get 10,920. So just some short examples of how this would work. All right. One final example with respect to binary. Now remember with binary, okay, there's only 2 outcomes with binary. Remember, it's either 1 or 0. Okay. So that might make it tough to be able to figure out the number of possible outcomes. So in this time we have 13 characters. So for letter A, I'm just going to draw the 13 spaces. I'll draw one under here. And notice for letter A it says repetition is allowed. So on the first draw there are 2 outcomes, and 2 outcomes, and 2 outcomes, and 2 outcomes, etc. Now this could be tedious, especially if we had many more than just 2. Alright, for instance, if we were doing hexadecimal, then this might be a little bit tougher. Or another easier way to write this would be 2 to the 13th power. And remember a little bit earlier we talked about the idea that if we know back when we did our decision tree. If we know the number of possibilities and it stays static, and we know how many times we're picking that, then we could just raise that. We could just say the exponent is going to be the number of ways or the number of times that we're picking, and the base is going to be the number of possible outcomes. Okay, so we'll go back down here. That's 2 to the 13th, and in my calculator I'm going to compute that really quickly, and I get 8192. Now what if there wasn't repetition? Well, this actually becomes a really easy problem, because the first draw or the first random selection, there's 2. Now it doesn't matter what you draw, there's only one selection after that, and then after you've drawn that one selection, there are 0. Okay, and it doesn't matter after that because the product is going to be 0. Alright, so there's actually 0 ways that you could pick a 13 character binary number or binary word that does not have repetition. Alright, so hopefully there's a number of different examples of this for the multiplication rule. The next thing we're going to talk about is an extension of this, is the idea of a permutation and the idea of a combination.